What is a lambda cube? Lambda cube is actually it's a system that classify different types of lambda calculus. Here in the corners of this cube, they have the different type of the lambda calculus, and these arrows show how can they transform one type of the lambda calculus into some other type of the lambda calculus by adding some properties. If you look here, you can see that they have the three types of the arrows in all these lambda cube. They have the horizontal arrow, vertical arrow, and z-axis arrow. So these types of arrows. Okay, and every arrow encodes some property which they add to the lambda calculus, which have position at the start of the arrow. And after they add this property, we will receive the new lambda calculus, which located at the end of the arrow. Okay, what they add? The horizontal arrows or x-axis arrows, they add ability to have types which depend on terms. Okay, also known as dependent typing. This thing. And on the y arrow or vertical arrow, they have ability to terms that can be bind to types, or in other words, the terms that depend on types, and this thing called polymorphism. And also we had the z-axis and this thing that provide to us type operators, so the types can depend on other types. And when you combine these three types of the errors, you will receive some point on this lambda cube. So actually you will receive some kind of type system. For example, here, if you take this, you start from this point, from the simple type lambda calculus, and add to it ability to of the polymorphism. You go up, and you will have this. You will build this type system in this corner. If you want also add the ability of dependent types, you go from this point to this point, and you here. And if you want from this point add the ability to have the type operators, you go the most rich type system lambda of construction, lambda calculus of constructions. For example, if we review the Haskell at this space, where we will find it? What Haskell has? Haskell has the ability of polymorphism. This means that they go from here up, and also Haskell has the ability of type operators, also known as type families. This means that they go here, but Haskell hasn't ability to have the at this moment it hasn't dependent types, so the types cannot depend on values. And we can say that Haskell somewhere represented here, but in Haskell we can simulate the dependent types with such thing as singleton types, and it can be seen as something, I think, here in the middle. Interesting that also the lambda cube doesn't contain all possible type systems, whereas exist more type systems. And there is some generalization of lambda cube, the concept of the pure type system. Interesting that there exists some relationship between the type system and a logical system. And here you can see this is 8 system of the lambda cubes in this first column and corresponding logical system. So this correspondence also known as Curry-Howard isomorphism. For example, here, if we look at this correspondence between this system and the first order predicate logic, let's find this system in the lambda cube, and you can see that it can be found here. So how we construct it? We take simplest lambda calculus, add to it the ability to this horizontal arrow, the ability to have the dependent types. So actually this is the types which depend on some terms, and it has correspondent to the predicate logic, okay? And what is actually the predicate? The predicate is some can be seen as some proposition that depends on the some object. Okay, you will put some object there and you will receive true or false. And you know that proposition can be reviewed as a type somehow. All the systems in the side cube have 3 properties. The first property is Church-Rosser property. It said that if they have some term that can be better reduced to some term n, and also by the some other path of the better reduction it can be reduced to some another term, and there exists some final term to which all these n and n prime can be reduced. So this means actually, in other words, that if the have some term at some point and they do the better reduction and they go into 2 ways, then sometimes actually all this we can go into some one point, final point to which we can reduce this term. And also the second property is subject reduction property. Actually it says that actually this say that then they do the better reduction steps, the computation save to us the type all this the same to the all steps of the computation. And the last property, the uniqueness of type. So our terms can have only one type.